What I'm bringing in is that, wait a minute, by modifying Einstein field equation, we might be able to solve for all this and not need so much quantum theory, which is quite a change in the optics. This is one of the things that Einstein believed all of his life. That's why he was never keen on quantum theory. That's why people say that he dropped out after he wrote his field equation. He didn't really want to participate anymore. He believed that with his equation, he should be able to solve all the way down to the subatomic particle, and he actually got really close, I believe, at one time, because a French mathematician contacted him that was giving him solution to his own equation that incorporated torsion. Torsion is the distortion of an object. If you apply torque to an object, imagine you have a 2x4, and you hold the bottom and you twist the top, you're going to get a distortion of the object. Okay, that's called torsion. And so this is Élie Cartan, thought that, you know, maybe we could solve Einstein field equation just by describing the torsion or the distortion of space-time around a gravitational field. And he solved it. The thing is he solved it, and it gives the exact same answer as Einstein field equation. So everybody said, well, it doesn't teach us anything more, and it's more complex, so they dropped it. The only thing is that in order for something to distort, you have to have torque in the first place. And that they never went to. They never added the torque to the space-time manifold. If you are missing 98% the mass of the universe, okay, you most likely missed the source of force that is creating what you are observing. And I believe that source to be space-time torque. Okay, the force that spins a galaxy. Imagine if you had to build a motor, how many horsepower you would need to spin one galaxy with 300 billion stars in it. A lot of force. Imagine how much force you would be missing if you didn't account for that engine. Right? That would be like analyzing the wheels of your car, okay, and all its dynamics, its mass, its angular momentum and everything, but omitting to add to the analysis the V8 engine that's spinning it. Now when you look in nature, you can see these dynamics. Look at this. This is a galaxy, okay? And galaxies have galactic halos. Can everybody see this? It's like a very fade, big sphere around the galaxy. And when, when we look at galaxy, typically we only think of the galactic disk, right? And that's because in the galactic disk, there's the most amount of density because the sphere around a galaxy has a huge surface, so things spread apart, so it's not as easy to see. But there's actually more stars in the galactic halo around galaxies than in the galactic disks. And then here you can definitely see a huge vortex going into the black hole at the center of the galaxy. We can't see the one below it because, these are very far away and we don't have that great of optics and so on. But we know that in general, there is always, or typically, two huge vortex going into center of black holes. In the case of our galaxy, that vortex is, I believe, 3 on the north pole of our galaxy, if you're looking from our perspective, is 3,000 light years long. 3,000 light years long. This is, at the speed of light, it would take still 3,000 years to get to the end of the vortex. And it's filled with gases and high velocity dynamics and high energy dynamics enough that it's actually visible thousands and thousands of light years away from it. Imagine how much torque you need to produce that. Isn't that an obvious example of water going down the drain? Okay, now you'd say, well, wait a minute, when we see these vortices and we follow the particles, they're spitting out. Okay? Well, okay, if water is going down your drain, air has to move out of the drain for water to come down. That's the exchange. We only see the outside of the event horizon. We only see the radiating part of the event horizon. We don't see the space-time torque going into it to force the system to have angular momentum. And so the result is that we live inside a black hole. That's why it's black out there at night. Okay? And what we see inside that black hole are smaller black holes, smaller scale black holes, that we're on the outside of. So what do they look like? Radiating stars. Radiating objects. Because we're on the outside, we're seeing the plasma Coriolis forces dynamics on the outside of the thing. We see the radiative side, we don't know about the contractive side, and that's why most of our physics is based on the radiation. But there's an exchange between the two, and this is the exchange I'm showing here, and that we calculated. These are very large objects, blazars, quasars. They're all being photographed to have these huge vortices. They're enormous. We see them at all scales. This is a quasar. So here you can see 10 to the 6 light years long is this vortex. That is 1,000,000 light years long. Okay? 1,000,000 light years long vortex. At the speed of light, 1,000,000 years to get to the end of it. And these things are spinning at near the speed of light when they arrive at the event horizon of the black hole. So very, very high torque. Big engines out there that are not being calculated. Now this is the different scale. Those are called microquasars. We find those even inside our own galaxy. And in this case, the vortex is only 3 light years long. So now you're starting to see the scalar dynamics, the scale change, the fractal nature of the division of space. From quasars to microquasars to cloud stars or supernovae, we see the same dynamics, the same vortex. Look at this vortex dynamic on this pulsar, which is the result of a supernova explosion. Have you ever seen articles in a layman physics magazine where it says the death of a star explode into a supernova? Okay. We haven't ever experienced the death of anything. We haven't observed that. We really haven't. All we've observed is things changing state. Okay? For instance, I'm not talking esoterically here. For instance, people have all sorts of debate about if life continues after death or eternal, whatever. You don't need to be esoteric. Just take, what you got and extrapolate from it. You have a few billion atoms. There's a lot of cells. There's 100 trillion cells in a human body. And they're all organized in an organized matter. And then all of a sudden, they disorganize. Okay? However, all these atoms are still spinning. You haven't lost one. Okay? They're still out there. They're still spinning. In fact, you might be made out of the atoms of your neighbor. And your neighbor might be made out of your atoms. And so there's no evidence that things actually stop. Because if there is space-time torque going to singularity in each point, then there's angular momentum at all levels and things continue spinning no matter what. What I'm saying is that the friction that's out there is overcome by the space-time torque. So, and that makes it appear as a frictionless environment. So we don't see death. We just see things changing levels of organization, changing scales. And when we see a star exploding, right, they call it the death of a star. But when they focus on that same area afterwards, what do they see? They see a pulsar. Oh, that's nice. They just changed the name from star to pulsar, so the star is dead and the pulsar is born. Let me give you an example. If you were a camera inside a woman's womb, and this woman was pregnant, you would see life developing in that womb. And after 9 months, you would have probably a pretty good relationship with this life inside the woman's womb. All of a sudden, there's a big earthquake in your world, and waters disappear, and there's an opening that opens in the little black hole at the end of this hip joint, and this being that you had a relationship with disappears through that hole. You would experience death. You would think this being is dead. The person on the other side experienced life crossing the event horizon. So what I'm saying is that our mathematics and our views have now shown us that actually pulsars and supernovae explosions are the result of stars. When space-time is torqued into a certain radius, and it generates material inside, so that the Big Bang is only one of those events that generated the atoms of our universe, that atoms are actually being manufactured at the singularity of black holes. And that's the exchange of those atoms coming out, those vortices, as the space-time torque influence those black holes. And when those particles get out of there, they are stuck in the gravitational field of that black hole and accrete on the surface of the event horizon, as well as other atoms that are created by that black hole as it travels through space. And when it accretes too much material, it becomes unbalanced. There's too much radiation for the contractive torque force at the center of the system. The system slows down too much, and the instability generates an explosion. It blows up. What it does, it releases a layer of material so it can regain stability. And so that's what we see. And then it regains stability, and when it does, guess what? The radius is much shorter, the ballerina has brought her arm in, so the thing spins way fast, like a pulsar. Okay? And then if it's fast enough, then we call it a black hole, and we say, look, the star made a black hole. And what I'm saying is, no, the black hole was always there. What we observe now is the dynamics of that black hole much closer to the event horizon, so we see the X-ray emission and all this stuff that we wouldn't observe before. By the way, all these things are X-ray emitters, from atoms all the way down to up to galaxies and so on. So do you see how the picture is a little different? Now we start to see the universe as cycles in space. Okay, instead of start, stop, start, stop. And you start to see that maybe, just maybe, that's how our universe was created. An enormous black hole that became unstable and blew up a certain amount of its orgosphere, a certain amount of its plasma, which generated all the rest of the stuff we see today.